In this video, we will perform triple integrals in cylindrical coordinates. Let's recall that for polar coordinates, we had that dx dy was equal to r dr d theta. And so the natural thing to do is, working in cylindrical coordinates, is to let dx dy dz be r dr d theta dz. So if I change to cylindrical coordinates, the z coordinate is left alone, but now the region in the xy plane is described in polar coordinates, r and theta. So let's look at an example of how this works. So we're going to consider a wedge of cheese with height 4 centimeters and radius 6 centimeters and an angle of pi over 6. So what I'm going to do is I'm going to start from the x-axis and trace out an angle that I believe is going to be pi over 6. And then I'm going to extend out a radius of 6 centimeters. So here, this is a radius of 6 centimeters in each of these directions. And this is an angle here of pi over 6. And then I'm going to let the height of this cheese be 4 centimeters. So here the height of the cheese is 4 centimeters. And then I'm thinking about that I took a cylindrical block of cheese and then I've cut out a wedge. So it's going to come across like this. And then it's going to go up like that and make a cylindrical cheese wedge. Or sorry, a cheese wedge that's cut from a cylinder, easily described in cylindrical coordinates. And so what I want to do is I want to find the mass of the cheese if its density, which is going to be rho, is 1.2 grams per centimeter cubed. So I want to find the mass. So the mass is going to be a triple integral of the density 1.2, and then I'm going to integrate dv. But dv in this case is going to be r dr d theta dz. And so my r integral is going to go from 0 to 6 centimeters because the radius extends out to 6 centimeters. My theta integral is going to go from 0 to pi over 6 because that's the angle that was involved. And then z, it goes from 0 to 4 because it has a height of 4 centimeters. And so this is a fairly simple integral. I can split it up into just an r, a theta, and a z integral because r, the function I'm integrating is 1.2r, and that doesn't depend on theta or z. So I can integrate from 0 to 4 dz. Then I can integrate from 0 to pi over 6 d theta. And then finally, I can integrate from 0 to 6 1.2r dr. So the integral from 0 to 4 dz is just 4. The integral from 0 to pi over 6 d theta is pi over 6. And then I'm left with 0.6 r squared that's going to be evaluated between 0 and 6. So this becomes 4 times pi over 6 times 0.6 times 36. Well, if I work this out, this becomes 72 pi over 5 grams. So I don't give a decimal approximation. I'm just going to leave it as 72 pi over 5 grams. And that is now the mass of my cheese wedge. Let's do another example, but this example I'm not going to specify in cylindrical coordinates originally, okay? And it says a solid T lies within the cylinder x squared plus y squared is equal to 1. So the first thing that I want to do is I want to draw this cylinder of x squared plus y squared is equal to 1 in the xy plane. And then it's going to extend up from 0, okay, to 4. Right there. Okay, so that it goes all the way up to the plane z equals 4. And then I'm going to look at the solid as being below the plane z equals 4, and then above the paraboloid z equals 1 minus x squared minus y squared. So I've got this paraboloid here, kind of this upside down bowl shape right here. And that paraboloid, okay, has an equation of z equals 1 minus x squared minus y squared. So I've got a cylinder. Inside the cylinder at the very bottom is this paraboloid. And I want to go between the paraboloid and then the top of the cylinder. You might imagine that this is like a peanut butter jar. So if you buy a peanut butter jar, a lot of times you'll notice that it's a cylindrical shape, right? But there's some sort of lip at the bottom, okay? There's an indentation at the bottom, right, that takes a part of the a part of that cylinder away from the volume. And so this is kind of like integrating over a peanut butter jar, okay? So that's going to be the solid that I want to integrate over. And then it says that the density of whatever's inside that cylinder at any point is equal to its distance from the axis of the cylinder. So the density is, as a function of x and y, would be the distance from the center, which is just the square root of x squared plus y squared. So that's that's going to be the distance from the axis of the cylinder. Okay, so that's the distance from the z-axis is x square root of x squared plus y squared. Another way we can think about it is we can think about it as rho of r just being r. Now, I'd like to, again, find the mass inside that kind of peanut butter jar. Okay, so I could describe this in rectangular coordinates. And I'm going to kind of do that first. So I'm going to integrate from z equals 1 minus x squared minus y squared to z equals 4. I'm going to integrate the square root of x squared plus y squared. And I want to integrate that dz. Then I would integrate dy and then dx, describing that circular region. So if we described a circular region of radius 1, you'd have this region here. Okay, so this is going to be x squared plus y squared is equal to 1. One way that you can do that is you can integrate from minus square root of 1 minus y squared, x squared, to square root of 1 minus x squared. So that's integrating from the bottom to the top first in y. And then we can integrate across in x, and that would be from minus 1 to 1. And hopefully what you're seeing is something that's quite complex to deal with in rectangular coordinates. Okay, so first of all, the function has that nasty square root in it. Okay, and then the region is described by all of these kind of nasty square roots. So I would rather describe this whole thing in cylindrical coordinates. So if I'm going to describe a circle, a full circle of radius 1 in cylindrical coordinates, I want to go from 0 to 2 pi, going around theta, and then r I want to go from 0 to 1, and then z I would integrate from z equals 1 minus r squared, because that's 1 minus x squared minus y squared is 1 minus r squared, to z equals 4. And then I can integrate r, and then I still have dz, and then I have r dr d theta. Okay, I'm going to go ahead and just write this as r times r dz dr d theta. So think about the fact that dz dy dx is getting replaced by r dz dr d theta. Okay, so there were a lot of places where I saw an x squared plus y squared. Okay, under the radical there was an x squared plus y squared. That just became an r. I had z equals 1 minus x squared minus y squared. That became 1 minus r squared. So this is a much simpler integral for me to do than the previous one. Okay, so let's see what the mass is going to be then. Okay, so we're going to integrate from 0 to 2 pi d theta. The theta integral is completely detached from the rest of the integrals, so I'm just going to bring that out. And then I want to integrate from 0 to 1. That's going to be the r integral. Okay, so 0 to 1 r squared. And then I've integrated that dz, so that becomes a z. And I'm going to evaluate that between 1 minus r squared and 4. That whole thing has to then get integrated dr. The theta integral is the integral from 0 to 2 pi of d theta, so that's just going to be 2 pi. Okay, I'm still left with the integral from 0 to 1 of r squared times, and then z evaluated at 4 is going to be 4, and then minus 1 minus r squared. I'm going to integrate that whole thing dr. So this becomes 2 pi, and then this is the integral from 0 to 1. I get 4 minus 1 is 3, so I'm going to integrate 3r squared, and then plus, because I've got 2 minus signs there, and that becomes a plus r squared, so this is going to become plus r to the 4th. And I want to integrate that dr. So this becomes 2 pi times the antiderivative r squared is r cubed, and then plus 1/5 r to the 5th. And I'm going to evaluate that between 0 and 1. So I'm going to get 2 pi times 1 plus 1/5. Okay, so that becomes 2 pi times 6/5, or in fact, that becomes 12 pi over 5 for my answer of the mass of the substance that's within this essentially a peanut butter jar. It's a cylinder with this bottom lip described by a paraboloid removed.